So now we're at the point in our course where we've created our tables. We know how to do our DDL. We know how to create tables. Our tables are filled in with data, and people are using our database tables. And then we start to notice that maybe we have a lot of redundant information in our tables, and we might want to, going down the road, take an existing table and maybe split it into two tables. So before we do this, we want to kind of analyze the table. So we're going to talk about a topic which is called functional dependencies. So if we had a table, let's say this is a table of students registering for a course. We have a student's registration number. We have another column with the student's ID. We have one column with the student's name, so that's probably not a good idea. We probably want a first name and a last name, but we just have one name. We have the name of the course they're taking. We have the teacher of that course, and we have the textbook of that course. So if two different students take the same course, two different students are taking the same database course, they're going to have the same teacher and the same textbook. So at this university, there's only one database course. You can have like two different teachers for a database course. And the algorithms course has the same professor and the same textbook again. Okay, so you might think it might be a good idea to have a separate table for course, teacher, and textbook, so you only have to write the information once. This way, if we had many students taking the same course over and over, and then we decided, oh, we have to change the professor. We need a new professor. You have to go all over this table and change all their names. So it would be nice to just change it once. Okay, so the idea of a functional dependency is basically if you had a table and you were given data in one column, you can then, using that column, tell the exact data in other columns. So for example, from the student's registration, 123-1, I can tell you the student ID, therefore I can tell you the student, and I can tell you the course, therefore I can tell you the teacher and the textbook. I can tell all the fields from that one field. So if I had the registration number, this arrow means I could then tell you what the student ID, student name, course, teacher, and textbook is. And it's a lot easier to just write column A tells us column B, C, D, E. Okay. Now it turns out that if I know the student ID, without knowing what they're registering for or anything about courses, I can tell you the student's name, just from the ID. So column student ID tells us the student's name. Another way of saying that is column B tells us column C. Or another way of saying that is column C is functionally dependent on column B. Okay, and then if I knew the course, I would know the teacher and the textbook. So we're saying column D will tell us column E and column F. Okay, so these are the functional dependencies of this table. So we'd like to know that stuff and maybe make some rules. We'd like to know some rules about functional dependencies. So, and then being good at these rules will help us in being a better database administrator. So we have what are called the Armstrong inference rules. So inference rule number 1 is the reflexive rule that says if y is a subset of x, then given x, then x would tell us what y is. So in other words, so that would mean if x was a set of columns, column A, B, and C, and y is a subset of that, column B and column C, if you knew A, B, and C, you would know B and C. That's all intuitively true. The augmentation rule is if x can tell us what y is, if you were then given a column X and a column Z, you would be able to tell me what Y and Z are, right? Because I'm just adding Z onto both sides. So basically, if X can tell you what Y is, if I gave you what Z is, you could say what Z is. So X and Z together would give you Y and Z. This is another one that seems a little intuitive, but just stay with me. These get a little interesting. So the transitive one is if column X, and this could be a set of columns too, if X can tell you what Y is, and Y can tell you what Z is, then if you had X, you could figure out what Z is. And then other useful inference rules, or the decomposition one. If x can tell you what y and z are, then x could tell you what y is. You're just ignoring z, basically. The union rule is x tells you what y is, and if x also tells you what z is, well then if you knew what x is, you would know both y and z. And the pseudo-transitive rule is, if x could tell you what y is, and w and x together, w and y together can tell you what z is, then x and w could tell you what z is. Because from x you could get y, and then with w and y, what you got from x, could tell you what z is. Okay, so these rules are basically, so hopefully these are intuitive rules, and the idea is that you could keep reapplying these rules to generate new rules. So for example, suppose this was true in one of your tables. Suppose you had a table, and from column x you could figure out what column y is, and from column x you could figure out what column z is. Suppose that was true about your table, and then someone came along and said, well, if that's true, then if I knew what x was, I could figure out what both y and z is. Now that kind of intuitively looks true, right? Right? This is saying, from x I could figure out what y is, and from x I could figure out what z is. Now if I had x, could I figure out both y and z? That seems intuitively true. But if we wanted to actually write software that keeps taking these rules and applies them over and over and over, and just to see through like artificial intelligence to see if this rule is true, we could do that. So we could say, take this first rule, x gives you y, that's a given rule, and x gives you z, that's a given rule. And now we use rule number 2 on line number 1, and we get a new rule that says, from x I could tell what x and y are. So rule number 1 was, if I know what x is, oh wait, if it's a subset, right? Is that rule number? Oh, sorry, rule number 2. Rule number 2. Rule number 2 says if x gives me y, then I can slap any other column next to it, and then x and z gives me y. So if I take rule number 1, x gives me y, then I could say having x and x gives me x and y. So x gives me x and y. Okay, and then the same thing here. Using rule number 2 on line number 2, I could say having x and y would give me y and z. X and y gives me y and z. That would be a true statement, because all I'm doing is taking what I was given and putting y's on both sides. So this is also a true statement from our table, from what we originally told. And then this last one, x gives us y and z by using rule number 3 on these two. So rule number 3 says if x tells me what x and y are, and x and y tells me what y and z are, then x will tell me what y and z are. And that's what this statement is. So basically it's like someone came along and said, you have a table where these two statements are true, and they're saying, and therefore this must be true too. And you want to verify, is this actually true? And we could just keep applying those rules until we prove to ourselves that that is true. So here's another example. Some of these are intuitive. You might be able to just read right from here and go, oh, it must be true. And it's easy to just go through the exercise to prove it. So if you had a column W, which tells you the exact value of a column Y, and you had another column X, which tells you the exact value of Z, then having W and X can tell you what Y is. So that seems pretty obvious. You don't even need X, right? If you have W, you can tell what Y is. That you already know. But we can say, okay, so our first two rules are given to us. W gives us Y, that's given, and X gives us Z. Now we can say that W and X gives us X and Y by using rule number 2 on line 1. So we're taking this line and we're basically putting an X on both sides. So that's a true statement about our table. And then X, Y gives us Y by using rule number 1. So we're basically saying that if I knew what X and Y is, I know what Y is, because Y is just the subset of X and Y. So that's also a true statement about our table. And then from these two true statements, if W and X gives us X and Y, and X and Y gives us Y, then having W and X would give us Y directly. So this is also a true statement. Yeah?
Are the subsets necessarily commutative?
So what,
Because like
that,
you have the like Wx equals xy in 3.
right,
So does that mean that Wx equals xw?
yeah, that would be true in columns too.
Okay.
Yeah, yeah, right, so,
okay,
flip
so
from- yeah,
okay, so
because it's
they're-
just sets,
gotcha.
the order doesn't matter in the columns.
Gotcha.
Okay, good. Okay. All right, and so you kind of get the idea. So another one is, suppose you had a table where these three statements are true. Does that therefore, I should kind of have a question mark over this because we're testing if this is true. If these three statements about your table are true, then we're saying here's maybe a fourth thing about our table that's true. And we're going to check. So we're given three statements. X gives us Y, X gives us W, and W and Y together give us Z. Now we can say X gives us X and Y. Well, we've done this trick before where we just take this first line and put X on this side and an X on this side. Two X's in a row just mean you've given the data twice. So yeah, we're basically saying using XX gives us XY from rule 2 on line number 1. Then we're saying XY gives us YW. That's by using the same rule 2 on the second line. So we're basically taking this line and putting a Y on both sides. So this is a true statement about our table. And then X gives us WY by using the third rule on lines 5 and 4. So if X gives us XY and XY gives us YW, then X will give us YW. So this is also true about our table. And then using rule number 3 on lines 6 and 3, combining these two together, X gives us W and Y gives us Z, so therefore X gives us Z. So yes, this is a true statement also about our table. So the idea is basically if you have a set of rules about your table, you might be able to learn more rules about your table. And the more functional dependencies we know, the more we have to take into account when we go to split up our table. Okay, so now let's look at another example. Suppose there was a table, and if you knew the value of column X and the column Y, it could tell you the value of Z. And if you knew the value of Y, it could tell you the value of W. And then someone comes along and says, well, if that's true, then if you knew X and W, you could tell what Z is. Now, can you tell intuitively, does this look like it's true or false? It looks false? Okay. What would your argument be that it's false?
Because while Y completely gives you W, W may not completely give you Y.
Y gives you, right.
But W doesn't necessarily give you Y, so you have X
Right, really,
part of
W
Y.
is almost giving us nothing, right? Because it's just, if we knew Y, we could figure out what W is, but W doesn't really help us. And X alone won't give us Z, we need Y. And Y, we can't get Y out of W, so it looks like it may not work. Now, how would you prove that this is a false statement? What you'd want to do is give an example where it's not true. So you're proving it by contradiction. So basically, suppose we had a table that had 4 columns, W, X, Y, and Z. We want to put data in our tables that follows these rules, but breaks this. So if we can put in data that's following this, well, then we have a legitimate table for our database, and if this is not true, then it breaks it. So we come up with 2 rows. We want, there's a little bit of a little guesswork here. But what we can do is we can say, we want every time X and Y, let's see, every time Y is a particular value, W needs to be matching. But that's true in this case, because Y, the 2 Y values are different, so it's okay that these match. And we want X and Y to uniquely give us a Z, but here the combination of X and Y are different, so the Z, it's okay that the Z's are different, because the combination of X and Y's are different. So this table does follow these 2 rules. we needed to contradict when X and W match. In this case, they're both 1 and 1, but in this case, they both produce 2 different Z's. So what we did, basically, to prove this is not true, you just need a 2-row table. And both rows follow all of this, but contradict this. And we could have used letters or numbers, whatever really matters. But yeah, so that we want a counterexample. A table that's following this rule and this rule, but doesn't follow that one. So if you gave an example where it said 2 and 2 here, it wouldn't prove anything. It doesn't mean this is true or false. Maybe we just came up with a bad example. But in this case, we got a good example. Okay. Okay, so all right. So we have a little, a little chat about rules on tables, and then based on some of those rules, we can make new rules, and then what I mean by rules is functional dependencies. So now we're back to this table. So suppose we had this table of students registering for classes, and we decided maybe we'd like to take this piece and make a separate table out of it. Maybe even have a table of students and their names, that could be a separate table, and then have a registration like this student is registered for this course, somehow join those together. So maybe we want to split this into 3 different tables. Okay, so the table may have the following functional dependencies. So we had this before, and suppose someone came along and decided to split the table like this. They decided to have one table with the registrations, basically saying this registration number is this student, and this is the student's name. And then another table with the course, the teacher, and the textbook. And of course, we have to join these 2 tables together because they have meaning together. So we need, in order to create a diamond in our design, we have to somehow join this table to this table. That could mean making a separate table with 2 columns. It could mean adding a column to one table that connected to the other table. So suppose the database administrator came along and said, I'm going to add a column to the table that has the course, teacher, and textbook. I'm going to add a column to connect it to the students who are registering for these courses. And what I'll do is I'll have the student name column added. And I could do a foreign key that says these students must appear here. Would this be a good way to join these 2 tables together? And if so, or if not, why?
Student name might not be a unique value.
Right. So if right. So what probably would have been a good column here?
Student ID maybe, or registration number.
Student ID.
A student may have more than one class.
Yeah.
You could just put the course name in the register columns, let's put database and algorithms, so leave off
Well,
the teacher and textbook. And
yeah.
the student classes have the database, teacher, and textbook.
Well, yeah, it might have been good to just have these 2, right? The course, teacher, and textbook in a table.
Yep.
And then if a student wants to register for that course, we'd have to have something that says this student is registered for that course, which might be a separate, so it would depend. Now, if it was a many-to-many, if a student can take many courses and a course could have many students, we'd probably have a 3rd table, a table in the middle that says this student is taking this course, right? We'd probably do that. But so what is the problem if we did do this, if we use the first name of the student to connect to this table?
How is it both classes? So
Right, so it looks like these are 2 different Mohammeds, but they would now be showing up in 2 different classes. So if we did, right, so this is what our 2 tables would look like, but to somebody looking at registration records, we now have 6 registration records. Because when you do the natural join, when you naturally join the 2 tables, you say, oh, what fields do they connect on? A natural join is going to put a pointer at this row, and then it's going to walk down every one of these rows looking for a match. So it's going to say Sandeep took this course, didn't take this, didn't take this. Now Mary took this course, and that's the only match. And then it's going to say Mohammed took this course, and this Mohammed took this course, and this Mohammed took this course, and this Mohammed took this course. And now the two records in red are not true, but now anyone querying our two tables will think that they took those courses. So this would be a bad way to break up this table. So this is like, yeah, this is what the tables really look like, but anyone using the database now thinks these students have registered for these courses. So that would be a problem. So that's a bad way to do it. Now, suppose it was a more complicated table and you couldn't see with your eyes that this is a bad way to break it up. So there's a property, it's a strange name to it, the lossless join property. And it's basically the property that says if you break up your table, you won't cause the natural joins to have records in them that never existed before. You won't create new registration. So what we want to do is when we break up a table, we want to, as the database administrator, we want to make sure that the breakup of the table maintains the lossless join decomposition property. So there's an algorithm for it. I'll walk through the algorithm first, and then maybe we could read through the letters of it. But, so suppose we had a table that had these functional dependencies. Column A tells us B, C, D, E, and F. B will tell us C, and D will tell us E and F, just like we had before, right? So we had student ID tells us the student, the course tells us the teacher and the textbook, and the registration number tells us everything. Now, if we decided to break it up the way we suggested here, which is not a good idea, to have them join together on the student's name, we'd have this algorithm. So the textbook describes the algorithm as for every column, make a table for every column in your original table, and then for every relation that you broke it up into, have a row for each of those. So we'll put in a unique symbol in each one of these boxes, and they use those letters small b and then the address 11, 12, 13, 14, 15, 16, 21, 22, and so on. Okay, and then we say, okay, now if the new table, the first relation, this one, column A, B, and C are together, and then on the second one, it's C, D, E, and F are together, then what we'll do for each one of those relations, we will use big A1, big A1, big A1, and then the second one will be big A2, big A2, big A2, big A2. And what we want to do is basically see if we can somehow connect all of them together so that from the two separate tables, we have exactly what appeared in the original table. So what we'll keep doing is we'll keep looking at these functional dependencies, and what we do is we say, okay, if B can give us C, then we'll look in this table and we'll say, do these two symbols match? And if they match, that means anything in the columns after it, we would make those match too. So yeah, maybe we'll go through two examples and then kind of get the intuition of it. So since these don't match, this rule doesn't help us. Since the values in the D fields don't match, we can't make these letters start matching. And then the A fields, since these don't match, we can't make anything match. So at this point, our algorithm stops, and we say that none of our symbols are across the board all capital A's. There's a couple of B's in them. So this one will not work. This decomposition will not work. Let me go over one that works, and then we'll take a look at the algorithm. Suppose I'm going to change the functional dependencies. Suppose column C, which was our student name, suppose column C uniquely gave us column D, and column D uniquely gave us E and F. That split would work, right? Because we'd have column A, B, and C, and then C would uniquely give us D, and D would uniquely give us E and F. So then we wouldn't have like the situation with the two Mohammeds. So for example, if this column uniquely told us the course, then there'd be no problem. Here, two different Mohammeds were taking two different courses, but if this column uniquely told us the next column, if the C column uniquely told us D, and D uniquely told us E and F, then splitting it using the C column would have worked, right? So, so suppose we had, so all I did was change this middle one, this middle constraint. Instead of B gives us C, I'm changing that to suppose C gave us D. And we decided to split the table the same way. A, B, and C is one table, and then C, D, E, and F was the second table. So we would put all our unique, the little b's here, then we'd say, okay, the A, B, and C become big A1, big A1, big A1. And then big A2, big A2, big A2, just like last time. Now we start looking through these functional dependencies and saying, can any of them give us the rest of the fields throughout the table? So A does not, these don't match, so that doesn't help us. We look at C, the two C's both have big A's, big A1, big A2. So what we can now do is go through everything that it gives us, which is the D column, and make these, if there's an A here, make them both A's. So the next step of the algorithm is to say, if I have any functional dependency, and what's on this side, on the left side, have big A's here, then what they give us, I'll make those, if there's a big A anywhere, I'll make those big A's. So that makes these two big A's. Now we keep going, we keep iterating over and over through all our functional dependencies. And we go to this one, the D's match. Since the D's match here, I'm gonna make these match. So this A2 gets written up here, and this A2 gets written up here, and we get this one. And if we ever hit a point where one entire row is all big A's and no little b's, then we know that that split worked. So it sounds like a complicated algorithm, but all we're really saying is, it's kind of intuitive. If these were the rules of your table, the split would work, because I'm putting A, B, and C in one table, and then C with everything after it in another table, and it looks like C and everything after it, C is the key to everything after it, right? Because C gave us D, and D gave us E and F. Therefore, C gives us the rest of the table. So therefore, it would work. And all this algorithm is doing is just trying to go over, because you could have many dependencies, and you want to just have a trail that says, I can get the whole remainder of the row from one field. So this top row is basically saying, A gives us, from this table, A, B, and C are uniquely identified in one table, and then C connecting to the other table, this is really the connection between the two, allows me to figure out uniquely what D is, that's what this step is. And then because D gives us the rest of the table, these match. And then eventually I've had one of them, I'm basically saying from the field A, I can uniquely get every field in now the two table split. So the algorithm is, the wording is a little strange, but now that we kind of went through it, maybe it'll make sense. So we create a matrix of a row for every relation for all the ways we split up the table, and a column for every entry that was in the original table. We set them all to little b, I, with the address, little b, I, and j. So we initialize them all to little b's. And then for every row in our table, if the column appears in one of the relations, we put a capital A with that field in it. So that's basically, I'm initializing everything to a little b plus the address of the box, B11, B12, and so on. And then I'm saying, because I have two relations, one is column A, B, and C, I put big A1, big A1, big A1. And the other table had C, D, E, and F, big A2, big A2, big A2. So that's basically, this is the first step, here's the second step.
So if you had three tables, it would be 3 rows.
Right, so that's important. So the original table had 6 columns. Now you could split it up as many ways as you want. With every table you split it up with is another row here.
Okay.
And we're tracking their connections to each other. And we're trying to see is, can I get from any one row, uniquely find everything else in the column, and then that would mean nothing new was created. The three little tables that you've created didn't generate any new records that weren't in the original one big table. Right, so this is step one, this is step two, and now we just keep running through these over and over and over just to see if the table changes. And once it stops changing, then we know we're done. So, right, we initialize everything to the little b's, and then for every column that is in one of our relations, we make a capital A out of it. And now we repeatedly follow this and do this over and over. For every functional dependency, every time you have a set of fields, gives you another set of fields in our table, we keep going through the table and basically saying if X gives us Y, we look through the X columns to see if they match. And if they match with a capital A, then we make all the rows after it also have a capital A. If they match with a little b, then we make them have matching little b's. And we just keep doing this over and over, and if we ever get a full row that is all capital A's, then we know the way we broke up the table will not falsely generate any new records, like two different Mohammeds are now taking every course together. We won't generate anything new. So the idea is when you're a database administrator, you have a table, the table's up and running, everyone's using it, and you decide for efficiency, I want to split it. You don't want to split it and generate records that really were never there. So you have to make sure that the way you decide to split it, you can test it and make sure that you didn't generate any new records. So you want to split it and not have this lossless join decomposition property. So in this case, we tested for it, and we never got a row that was all capital A's. So therefore, we made a mistake when we decided to let column C be the ones that connect them. But if it just so happened that C gave us D, then splitting up the table into A, B, C, followed by C, D, E, F would have been a legitimate split of the table. That would have had this property.
Can you simply say A, C, and D have to be your keys in the table?
A what?
A, C, and D have to be keys in your table?
If, well, yeah, actually, so intuitively, if C was well, C wouldn't need to be a key for the whole original
A
table.
would need to link to C, which would give you D, and then D would need to be
Right, that's
and then
really
C.
the intuition to it, in that if A can uniquely connect you, if from A you could get C, and from C you could get the whole second table, then really from A you could get the whole original record. And that really is at the heart of it. It sounds like this complicated algorithm with big A's and one thing I never quite understood is I don't even know why the addresses are needed. I think if you just put little b's and big A's, it would work fine. I don't think it ever mattered what those numbers were. I think the algorithm would have still worked
I think
fine.
that the indices B is in the second column, second row. So for B22, it is like second column and second row.
Well, no, it's just telling you where it is, but I'm just saying, I think if we just if we started off with a whole row of little b's, and then put some big A's, and then anywhere you see two big A's, you make all the other ones big A's, I think it would work anyway. It just seems like a lot of notation. These ones and two, I don't know if they're needed. I think it just overcomplicated the algorithm. But yeah, all we're really trying to do, because there could be a lot more, you could have a table that had 50 columns and that could be 20 functional dependencies, and it's just too much, for the mind to keep track of. So basically you build this table and you just keep going over the functional dependencies over and over and over to see if you could make more of the capital A's until you fill up a whole row. And then that would let you know this breakup of your table generates the same data from the original table. Okay, and then, and then just, so our last slide, this will kind of kick off our next talk, is basically putting your database into what's called the voice card normal form. So whenever there's a functional dependency, X gives you A in a relation R, then X is a superkey of that relation. So the idea is to try to not have these situations where you have a table. And some columns in the table, like even the registration number, actually has hidden in it the student ID. It's kind of like the student ID -1 and 2. So this number can give you this number, and this number can give you this number, and this number tells you this number, and then this field tells you this number. We shouldn't have that scattered all over the place. In Boyce Codd normal form, there should be one column that uniquely tells you everything else, and nobody else is dependent on anything. So it's kind of like saying this should be broken up into a separate table, these last three, and this should be broken up in these two together. This student has this name, this should be a separate table, and then using keys to join them all together. So we'll go through these normal forms. This is like, oh sorry, this is like the final normal form. There's kind of like a first normal form and a second normal form and a third one, and each one gets a little bit better, and then finally if you get it to this form, that's where you'll have the least amount of redundant data in your tables. So yeah, so we'll go, and our next thing will be go through all the different normal forms.